So let's look at the choices first that we have in terms of this first ingredient, which is the discretization. We already said that the finite volume method can handle any type of mesh, and so there are a variety of ways in which we can relate the control volumes that we're going to use to apply the conservation laws to a mesh, to a set of lines and points that we can construct. So we can have, for the same mesh, different definitions of the control volumes. We can have a few options. The first one is called a cell-centered scheme. So suppose that we have something, remember it doesn't have to be a Cartesian rectangular, and so we can sort of have a skewed mesh, something like that. Let's see, I'm going to try to draw something that is skewed but still regular in this case. For example there, and this is our mesh, which is still structured, but these are our mesh points, the intersection of the mesh lines, and this is just a little piece of the mesh, something like that. And so in the cell-centered scheme, we would have in the center of the cell, this would be our point ij, and so the one on top would have a point ij plus 1. So j plus 1. So what we're saying is that the control volumes are identical with the grid cells, but the flow variables are located at the center of the grid cells. All the flow quantities are located at the centers of the grid cells, and the grid lines define the control volume surface. So because the flow variables are located at the centers of the grid cells, it means that they are a averaged value over the grid cells. So if this is my grid cell, and I'm looking at the point ij, any variable, for example, uij, is actually an average. In the grid cell. Same for any other quantity. Another approach is the approach called the cell-vertex scheme. And here we would have something a little bit different. For example, again, let me draw perhaps an obvious, let me just draw perhaps again, a mesh, not necessarily, as before, not necessarily uniform, but or Cartesian, but we've drawn this to be structured at this point, and let's consider now that point ij is here in the middle, and so associated with point ij, we're going to have all of this volume here. And this is point ij. And so basically we're considering the 4 cells which have the mesh point ij in common as our finite volume. Notice that if I define them this way, the control volumes could potentially overlap. Because I could have point I here, I plus 1, j, and for this point, the 4 cells are this one, and the other 2 that I haven't sketched over here. Okay? They can overlap. They would overlap in this scheme that I've shown here. And there are many other choices possible. For example, I could have something, let me draw some other options. Let me draw something just more easy. I'm going to draw it just a little bit more regular, just to make it easy on me. And I'll do these lines, I'll skew them a little bit. And suppose I have as my mesh point now this guy over here. Well, let me choose, oh yeah, I'm going to choose this one. And the finite volume is going to be a volume that goes like this. Perfectly appropriate, acceptable to do this. And then I'm using the diagonals here. And this is the volume associated to this mesh point here. That's perfectly acceptable too. This would be sort of like a hexagonal control volume. And another approach still could be, I could have here's my mesh, oops, more or less. And I could assign to this mesh point a control volume that goes to the midpoints like that. Or I could even have it go all the way up to here, and just the midpoint on the I index. That would be okay too. A trapezoidal one would be like this. This is another option. I could just go to the midpoints like that. And that would be a trapezoidal control volume. And that is also acceptable. So there's really many, many choices possible. This illustrates the flexibility of the control volume. But there are some requirements for the scheme to be consistent. We already realized that we need the internal fluxes to cancel, so that requires some restrictions. The first one, of course, is that we want the sum of all of the control volumes to cover the entire domain. Okay, that seems obvious. All the control volumes should cover the entire domain. We also, well, suppose that we're using subdomains that I'm going to call omega j with a capital J. And these subdomains really could potentially overlap. They are allowed to overlap. There's no problem with that. But this, as long as each portion of the surface, portion here, let's call the surface S J. Each, in this two-dimensional case, of course, the surface is the lines. So this is are the geometrical, locations where there is a flux. All of these surfaces, in general, I'm calling them surfaces, have to appear as a part of an even number of different subdomains. Such that when I'm going around the surfaces of one and then going around the surfaces of another, they cancel out. We need that, right? So we want overall integral conservation to hold for any combination of adjacent subdomains. If I choose any subset of subdomains, it should still satisfy the conservation law. And for that to happen, the surfaces need to appear in an even number, and of course they will be with a different sign depending on which cell I'm looking at. So that is the other requirement, and the final requirement is that computing fluxes along a cell surface has to be independent of the cell in which they are considered. Again, this guarantees that they will cancel, all the internal ones will cancel out. So we compute them in the same way for every cell. So this is the way that we ensure that conservation is satisfied and all the flux contributions of the internal boundaries cancel. So if I have two subdomains that overlap, for example, I could have for this one, I've drawn it in red here, and then for the other point down here, I would have this one, so they overlap. With the one on top by this part over here, but the surfaces appear twice. This surface appears in this guy and appears in the one on top, of course. And they cancel out. Okay. So all of this discussion was about the first ingredient of the finite volume method, which is the construction of these spatial discretizations. And now let's look at how we would discretize the equations themselves. The finite volume discretization of the equation. So we want to apply the integral conservation law to each control volume. Our integral conservation law that we wrote before, d dt of a quantity u d omega plus the flux terms s. I'm going to use now omega j and sj to indicate that these are subvolumes. And so in a discrete form, I'm going to use ddt. These volumes are small, so I can use some sort of average quantity, u average j, multiplied by the volume of j, plus the sum over all the faces of the volume j, f times delta surface is equal to some sort of average again of the sources multiplied by the volume of the small volume j. So this is with u bar j and q bar j representing the average values over the cell. So if the integral form of the conservation law is integrated in time, between time level n and time level n plus 1, then we could write u bar j omega j at n plus 1 is equal to u bar j omega j at n minus delta t. Suppose that we use a Euler method for time sum on all the faces of, let's call this f star, which is going to be our average flux plus delta t q bar star. I'm going to write what this is in a moment. Times the volume. So now our cell average values, I'm going to write them out. The cell average values that we have there, u bar j, q bar j, and also the star values are integrated in time. So let me write these out in the next slide. If you've got all that done, you've got that equation down, okay. So the cell average quantities are u bar j. We define the average by 1 over the volume j and the integral of u over the volume. And if I'm looking at time n, this would be all at time n. And so on, depending on the time level. Q bar j is 1 over omega j, integral over omega j, q d omega. F star dot delta s represents 1 over delta t, integral between n and n plus 1 of the flux and this q bar star j is 1 over delta t, integral between n and n plus 1 of q bar j dt. So in the previous equation, the long equation that represents our discretized form of the conservation law for each control volume, we omitted the time index on the balance of fluxes and the source terms. The reason we omit that is because if we choose n, it will be an explicit method. If we choose n plus 1, it will be an implicit method. So we could choose either. Okay? So on this, guys, on this guy over here, and there was a sum of these guys over all the faces, and there was also a term that involved this also in the previous equation. The balance of fluxes had the sum over all faces of F star times delta surface, that's the balance of fluxes, and the source terms had delta t times q bar star times the volume. And this is to indicate, we omitted to indicate the choice that we have of n, and we get an explicit scheme. Or n plus 1 for an implicit scheme. And there going to be a variety of different schemes that we can use for the finite volume method, and the particular scheme that we may choose is going to be identified by the way that we approximate the fluxes, okay, in the equation. So a particular scheme, finite volume scheme, is identified by the way the numerical flux F the flux vector star approximates the time averaged flux, the time averaged physical flux across each cell. Cell surface, cell face. So if we leave open the choice of integration, we would write ddt, integration in time. We'll just leave this open. We could in the previous slide we wrote it if we used a first order Euler in time, but we could use other schemes. We could use Runge-Kutta or something different. So leaving that open, we have u bar j omega j equal to minus the sum over all the faces of f star dot delta s plus q, the sources, j, omega j, and sometimes all of this right-hand side is lumped into one expression, which is called the residual. It's just notation. Rj. So the residual Rj is simply the balance of the fluxes over a cell J plus the source contributions. Now we're ready to write some finite volume formulas.